Okay, so welcome to Specialist Maths. Yay! Week 7. Week 7, we're continuing on with complex numbers. So hopefully you enjoyed week 1. And in your imaginary little world, you know that I squared is equal to -1. Oh, and here's a little joke for you. Can you get it? Do you get it? Do you get it? What do you think? Thank you, Gabby. Somebody's laughing. Yeah, thank you, Levi. Isn't it cute? Neil's got a t-shirt with this on and he wears it shamelessly. I love it too. It's funny, isn't it? Okay, so let's talk about De Moivre's theorem. De Moivre is an interesting character if you want to Google him. Apparently he couldn't afford to go to university, so he just used to hang out with mathematicians and come up with theorems, which is pretty good. Okay, so we're going to just review a few bits and pieces before we talk about De Moivre's theorem. Chiefly, the main fact that we need to keep in our mind is that every time we see an I squared, we need to simplify it to -1. And there's a few other things we need to revise. When we see we need to solve complex numbers in the domain of C, that means complex numbers are represented by the domain of C, and we might be asked to solve polynomials in the domain of C, which means we will have complex solutions, as distinct from when in math methods you're asked to solve polynomials. Usually you're asked to solve them in the domain of the reals. And we have a way of representing imaginary numbers on an Argand plane. So the horizontal axis represents the real component of the imaginary number, and the vertical axis represents the imaginary part of a complex number. So we can represent A plus BI as having two components, a real component and an imaginary component. And Z is often used to represent any complex number. Not sure why. Must be historical reasons. So we can look at, if this was our complex number, Z is equal to A plus BI, the real part of that complex number is the A component. The imaginary part of the complex number is the B component. The modulus of that number is the distance from the origin, found by good old Pythagoras. And the argument is the angle made by the number with the real axis. So you can work that out by just using a bit of SOHCAHTOA, using arctan to work out that angle, and then you've got to adjust that angle so that it is within the defined domain for complex numbers in polar form. So if it's in the second, third, or fourth quadrant, you might have to adjust it and make sure it's within, the final result is within this domain using properties of symmetry. Okay, so that's a recap of last week. Oh yes, there's theta. Oh, I popped in at the last minute there. Okay, so we did a bit of look at some patterns that we get. Okay, so that's really important. So you can see that you can, if you got I to the power of, 27, you can actually simplify that quite a lot. How could you simplify that? How can I rewrite that? There's many ways I can write that. I can write that as I cubed, to the power of 9. Well, or I could, there's lots of ways I could write it. I cubed to the power of 3. I don't know. To the power of 3. Gosh, there's lots of ways I could do it. Or I could do a nice even number. Or I could go I to the power of 26 times I. Okay, maybe that'll work. Or I could write I to the power of 24, because I can see here, and then put I to the power of 3, because I can see here that any factor I to the power of 4 is going to be equal to 1. So that's 1 times I to the power of 3 is times negative I. So I should be able to get that answer by just playing around with the indices and knowing the index laws, etc. Okay, so Gabby, I'm glad you got the same answer as me, but you used a different set of index laws. That's okay, still good. Alright, so let's have a look at one we're going to simplify. We're going to try a few of these. Let's simplify I to the power of 17. I think I've already done it here. Oh, gee, that was cheating, wasn't it? So you can see here, I've used that little fact here, and I've just turned this expression using the index laws. I've just rewritten it. I to the power of, that's equal to I16 times I, and I16 can be written as I to the power of 4 to the power of 4 times I, and voila, easy. What about the next one? I to the power of negative 4. Now we're going to do that. Have a think. Left that one for you. It's equal to 1. Yes, Marco, because you can rewrite that, the index laws, when it's a negative power, it just means it's a fraction. So that's going to be rewritten. You can rewrite that as 1 over I to the power of 4. We know that I to the power of 4 is equal to 1. Voila! Ta-da! Okay, so the interesting phenomena of multiplying complex numbers by I. We have these interesting geometric rotations that happen. So when we multiply any complex number z by I, we end up with an anti-clockwise rotation of that number by 90 degrees. So if we keep on doing that, we can just keep on rotating where the number is, move it from one quadrant to another, and if we end up multiplying it by I to the power of 4, that's the equivalent of multiplying it by 1. We get back to where we started from. So isn't that kind of cool? It's kind of cool. Okay. Alright, so let's talk about De Moivre's theorem. Now I think some of you have already read ahead. It's not very difficult. It kind of builds on the ways of doing multiplication with polar numbers. So yeah, like I mentioned, De Moivre wasn't a mathematician. He was just a guy that used to like hanging out with mathematicians. But he came up with this theorem, which is pretty good for a guy that's just hanging out with mathematicians rather than, you know, I think he couldn't afford to go to university, so just used to hang out with them and have chats. So basically his theorem goes like this. So if you can express a number, a complex number in polar form, like r cis theta 1, right? If you put that to a power, say the power of n, raise that polar complex number in polar form to the power of n, this is the rule for evaluating the answer. The modulus is raised to the power of n, and the angle or the argument is multiplied by n. So you end up with r to the power of n cis n times theta 1. Should be 1 there. Okay, and underneath you know that cis theta is short for cos theta plus I sine theta, and underneath is the longhand form. So this is pretty handy because it makes, when we want to put a complex number to a power, it's far easier to do it when it's in polar form. So we want to often do that, or maybe sometimes, oh here we go, there's a summary there. And maybe sometimes we want to give the final answer in Cartesian form. So we've got to be able to convert between the two forms quite easily, polar and Cartesian. So just to recap, what we did last week, we looked at the product rule. So the product of two complex numbers in polar form is the product of the moduluses and the addition of the arguments. The quotient of two complex numbers is the quotient of the moduluses or moduli, and the difference of the arguments. And De Moivre's theorem just builds on basically the product form. I don't know, perhaps he invented the product form too. Basically that's an extension of the product rule. Any complex number in polar form, you raise it to the power of n, the modulus goes to the power of n, and the argument is multiplied by n. And then of course you've got to adjust the argument so it's within the required domain for the final answer. Okay, so let's use it now. So here's an example I prepared earlier. Okay, so we've got a complex number already in polar form, and we want to find z to the power of 3. Pretty easy. We're just going to apply de Moivre's theorem, which says we need to, if we're raising a complex number to the power of 3, we just raise the modulus to the power of 3 and multiply the angle or the argument by 3. Okay, so we end up with an answer, and is that the final answer, everybody? Is that the final answer? Am I happy with that? No, Marco, you're right. Why? What's the problem? I've got to think about where 5 pi on 2 is. Oh, that's my pen. Where is 5 pi on 2? Well, that's pi on 2. That's 3 pi on 2. That's 5 pi on 2. Yes, it's outside the domain. So I've got to adjust it. I've just got to think about where it actually is, where 5 pi on 2 is on the Argand plane, and adjust accordingly the argument so it's within the restricted domain. So it's the equivalent of, it's negative. It was negative 5 pi on 2. I should have gone the other way. So that's negative pi on 2, negative 3 pi on 2, negative 5 pi on 2, which is the equivalent of negative pi on 2. So now it's adjusted and it's all correct. Now I might want to convert it to Cartesian form for my final answer. So in Cartesian form, 8 cis negative pi on 2 expands to be 8 cos of negative pi on 2 plus 8 sine negative pi on 2 times I. So I just simplify all the components. The real part is 8 times 0, and the imaginary part is 8 times negative 1 times I. So in Cartesian form, z cubed, I could find the answer quite easily. Okay, or I can simplify the answer, the final answer in this case. Okay, so, alright, so what's actually happening here? So here's a number that you're really familiar with, the number 4. Now, the number 4 is a number that you're really familiar with, but you can express it in polar form in a way that maybe you haven't seen before. So 4 can be expressed as a complex number as well. 4 can be expressed as 4 cis 0. Does this make sense? Because if you expand cis 0, that's equal to 4 times open bracket cos of 0 plus I sine of 0 close bracket. Does that make sense? So it's pretty handy that you can do that. So you can express any real number in complex form and complex polar form. So 4 is basically equal to 4 plus 0i, for example, which is what you get when you expand 4 cis 0. Okay, hopefully that makes sense. So we're going to use that, and we're going to see that that's where 4 is. That's 4. That's 4 plus 0i. Okay, we put that on the Argand plane. Oops, that's where it is. And yeah, we've got negative 4. That's on the other side there. Negative 4 is over here. Negative 4 can be expressed as 4 cis of pi. Notice that this modulus is always positive because that's always the distance from the origin. The only way you can get a negative number in this way is to adjust the argument. Does that make sense? So we've got negative 4 here plus 0i. And negative 4 is equal to 4 cis of pi. Okay? Show that to your methods friends. They'll be totally confused. Okay. Alright, so that's really important because you can actually find, in the complex domain, you can find more roots of numbers than you can in the real domain. How about that? So, just by using De Moivre's theorem. So we've got here, say we have a positive integer n, and you have a complex number, w, that's equal to a plus bi. That's expressing it in Cartesian form, or we can express it in polar form, the same number. W is equal to k cis of beta. And it's the nth root of a complex number. Say it's the nth root of the number z. So that means w to the power of 9 is equal to z. That's what the, w to the power of n is equal to z. That's what the nth root is. Okay, does that make sense? W to the power of n is equal to z, and that means that w is the nth root of that complex number. And say the complex number z can be written in Cartesian form or in polar form. So we're just going to look at De Moivre's theorem here. So we've got w to the power of n is equal to z. Okay, and z is equal to x plus yi in Cartesian form. Now finding the nth root in Cartesian form is really, really difficult, but we have De Moivre's theorem. So we know that from De Moivre's theorem that w to the power of n is equal to z, and w can be expressed as a plus bi to the power of n is equal to z. Or, in polar form, we've got w to the power of n is equal to z, which is r cis theta. In polar form, we've got k to the power of n times cis of n beta, this is just using De Moivre's theorem, is equal to r cis theta. Okay, this is just all definitions now derived from De Moivre's theorem. So we can use that to find the nth root of a complex number. So here's De Moivre's theorem again being used to find the nth root rather than raising something to a power. It's kind of the same thing really. Okay, so that's really important because we're going to use De Moivre's theorem to find the nth root of a number. Okay, so here's a number you might be familiar with, root 2. Root 2. What's this? What am I doing here? I'm not sure what I'm doing here. No, you're familiar with that. You're also familiar with, De Moivre's theorem, the nth root of a number. So we're going to use it to find the 6th root of 8. So in this example, I've already worked it out, right? And how do I know that I've worked out the 6th roots of 8 here? All I have to do is raise each one of these to the power of 6, and I should end up with 8. So let's just try it, hey? Root 2 to the power of 8, or 6 I should say, is equal to what? Did you work that one out? What about this one? Root 2 cis pi on 3, to the power of 6. What's that equal to? A bit of De Moivre's theorem. What about this one over here? Root 2 cis 2 pi on 3 to the power of 6. See where I'm going here? Oh no, what about negative root 2 to the power of 6? Okay, let's think about it. So root 2 to the power of 6, that's the same as saying 2 to the power of 3. Okay, so we're happy with that, that's 8. Okay, what about some of these other ones? So that one's cool. What about root 2 cis pi on 3? That's going to be the same as root 2 to the power of 6, which we know from the previous calculations we did is okay, and that's going to be cis 2 pi, because we just multiply pi on 3 by 6. So cis of 2 pi is basically the same as cis of 0, which is the same as 8 as well. Happy with this? So we've done this one, we've done that one. What about this one? The one in the second quadrant here. That's root 2, according to De Moivre's theorem. That's going to be root 2 to the power of 6 for the modulus. And then that's going to be cis of 6 times 2 pi, that's 12 pi on 3, which is the same as cis of 4 pi, which is also going to be equal to 8. It's 4 pi going around 4 pi, takes us back to the original position if we express that as an argument. Okay, what about this one? Negative root 2, that's going to be the same as 2 to the power of 3 as well, which is 8. We're all happy? And I'll leave you to work these ones out for yourself. So we have 6 numbers that are the 6th root of 8. And we can check that we're correct by raising each one of those roots to the power of 6 and seeing if they equal 8. Now, one thing about them, they're evenly spaced around the origin of on the Argand plane. So this is one way of working it out. So if you're asked to work out the nth root of a complex number, they are always separated evenly. They're always evenly distributed around the Argand plane. So you can work out all the roots, their location by starting off with one of them. So you work out one, possibly the real ones are the easiest ones to work out first, and then you can work out all the others by just adding 2 pi over n to each one to work out the new ones. That makes sense. Okay, let's just see some examples. Okay, so we've just done that one. So 8 can be expressed as 8 cis of 0. So we know that if we're going to find the 6th roots, we're going to have 6 roots evenly distributed around the Argand plane, and we can give them a name when we're showing our working out. We're going to let the 6 roots be Z1 to Z6, and we work out the first one. That's really easy to work out the 6th root of just plain old 8, which is a real number usually. It's a real and a complex number. It's pretty easy to work that out, and we can express that in polar form as a complex number. So remember, De Moivre's theorem says if you want to find the nth root of 8, you've got to just raise that 8 to 1/6, which is the same as saying, which is going to be following De Moivre's rule. That's the modulus is raised to the power of 6, and the angle is divided by 6, which is what this is. So this is going to help you find the first root to get you started. So this is going to find the first root Z1. Hopefully that makes sense. And then we just know that all the roots are 2 pi over 6 radians apart. So then we can just add the angle. Okay, so we know that the modulus is always going to be root 2, and we just add that angle to the angle 0 to get pi on 3, because 2 pi over 6 is equal to pi on 3. So this gives us Z2, second 6th root, and then we add pi on 3 to that one, which gives us Z3 over here in the second quadrant. We add pi on 3 to that one, which gives us Z4 over here, which is the same as negative root 2. We add pi on 3 to that one, and we end up with the 5th root. Z5 is equal to root 2 cis pi on 4 pi over 3, sorry. And then we add pi on 3 to that angle to get the final one. So we've got all 6 now. Okay, and then we have to make sure that our final answer is simplified so that the argument is in the correct domain. So you can see here we've got a few little problems here with Z5 and Z6. What's the problem with those? We have to re-express them. We've got to make sure that the argument is between negative pi and pi. So we need to adjust these ones here as our final answer. But while we're showing our working out, it's correct to do this, okay? It's correct to show this. This is part of the working out, then we finalise the final answer and present it in the correct form. Okay, so we can actually work out the nth root of 1. Gee, why would you be bothered? This is something that's sort of kind of fun, I suppose. I'm not sure. But you can work out the nth root of 1. How about that? So you can say z, any complex number, like to any power, z to the power of 20 equals 1. You can work out the 20th root, just for fun. There's going to be 20 of them evenly distributed around the Argand plane. But I'm not going to make you do that one now. Okay, here's one I prepared earlier. And there's 3 now here. There's 3 answers. What do you reckon I'm going to ask you for here? There's 3 values around the Argand plane. What do you think I'm going to ask you for? The cube root of 1 in the complex number plane. If I was just sticking to the real number plane, the cube root of 1 has only got one answer, 1 cubed. It equals 1, right? But if I go into the complex domain, it gets a little bit more interesting. There's actually 3 complex roots of 1, of cubic roots of 1. So that's the simplest one to find. This one that's on the real axis here is the simplest one to find, but we can find all the other ones as well. Okay, what about, this can even be extended even further. How many roots what have I got here? What am I doing here? I've got 1, 2, 3, 4, 5. What am I asking you to work out there, you reckon? The 5th root of 1. Yep. So z to the power of 5 equals 1. So these roots are 2 pi on 5. They're evenly distributed around the Argand plane, around the origin, at an interval of 2 pi on 5. And the cubic roots of 1 are 2 pi on 3. That's there. And you can express them in polar or Cartesian form, but it's easier to work them out in polar form. Okay, I've got an example. Here's an animation here showing all the different roots. This goes up to, I don't know what it goes up to, 11, 12, 13, 14, 15, 1, 2, 3, 4, 5, 6. It's kind of nice, isn't it? So these are all relative to the origin. They all have a modulus of 1. And the only thing that's changing is the argument here. So you can see when we've got, so this is 1 here, and sometimes negative 1 appears there. Okay. Oh, I should actually draw the real and the imaginary axis here maybe. I don't know. So that's the real. And there's the imaginary. And you can see there all the roots of unity up to, just watch the animation again, what does it go up to? X to the power of 12 or something. 12th roots. Oh, 13, 14, 15. So yes, it goes all the way up to 15. That'll kill a bit of time, but it's kind of fun to think about this this property that complex numbers have. Okay, so let's use that to actually find the cubic roots in the in the complex number system, or numbers that maybe you hadn't really thought too much about before. You thought they were kind of easy. So here's the cubic root of 8. We're going to work out, we want to find the roots of 8 in the complex number system, the cubic roots of 8. So z to the power of 3, what are those z's that are going to be raised to the power of 3 that will give us 8? So first of all, we've got to express 8 in polar form. So 8 is 8 cis 0. We know that we are looking for 3 roots, and they are 2 pi over 3 radians apart. And we're going to use De Moivre's theorem to work out what they all are. R is the modulus. It's always positive. The only way to get a negative value is to make the argument. Okay, so I can see Marco's already got the answer here, and I think it's pretty easy to see. We can find, we're going to have 3 roots. Let's call them Z1, Z2, and Z3. The easiest one to find is the real one, of course, the one that r cubed cis 3 theta is equal to 8 cis 0. So that's the easiest one to find. That means that r is equal to 2 and theta is equal to 0 according to De Moivre's theorem. So that's the very first root. That's 2 cis 0 is the first cubic root. And then we just add 2 pi on 3 to that root until we have 3 altogether. So Z2 is just 2 cis 0 plus 2 pi on 3. And that's okay because the argument's in the correct interval. Then to find the third root, we add 2 pi on 3 to the second root. We end up with 2 cis 4 pi on 3, which the argument is not in the interval required, so we've just got to adjust that. And now we've got the 3 cubic roots of 8 in the complex number system. So we can express them in polar form correctly, and we can convert them to Cartesian form if we're asked to. Okay, so just got to be careful what the question's asking you to give the final answer, whether the final answer is expected to be polar form or Cartesian form. Okay. Alright, and that's what it might look like if you put it on the Argand plane. So you've got Z1 here, Z2 is in quadrant 2, and Z3 is in quadrant 3. And all of those numbers raised to the power of 3 are going to give you 8. All of it. Oops. Because that's what we're solving here. Okay, that's a quick way you can check you're on the right track. Okay, you can quickly check that you found those correct values. Okay, so what about z cubed equals negative 8? Okay, we can express negative 8 in polar form by thinking about where negative 8 is. Where is negative 8? Well, negative 8 is over here. On your real and your imaginary, the Argand plane. So you can work out what that is. That's basically the modulus is 8, but the argument is pi. Okay, so that's going to be expressed as 8, positive 8. The modulus is always positive, and the angle informs you which quadrant it's in. Okay, so that's going to be cis of pi. So there are 3 roots, and again they will be 2 pi over 3 apart, and we're going to use De Moivre's theorem to work those out. The first root, let's call it Z1. The second root, let's call it Z2. The third root, let's call that Z3. The first root's easy to find. R cubed cis 3 theta has got to be equal to 8 cis of pi. According to De Moivre's theorem, that means that r is equal to 2 and theta is equal to pi on 3. So this is the first root, Z1 is 2 cis pi on 3, and then we just add 2 pi on 3 to that first root to get the second one. That's 2 cis pi on 3 plus 2 pi on 3, that's 2 cis of pi, and then we add 2 pi on 3 to the second root to get the last root, the third root. It's 2 cis of pi plus 2 pi on 3, and we've got 2 cis 5 pi on 3, which we need to adjust so that we're in the correct interval for the argument. So we can re-express z subscript 3 as 2 cis negative pi on 3, and we can then give our final answer depending on what we've been asked to do. We've got the 3 roots, 2 cis pi on 3, 2 cis pi, 2 cis negative pi on 3. Or in rectangular form, we can convert those, and we can show them on an Argand plane. So there they all are. Maybe I'll pick a different colour. So this time we had, this one was Z1, this one was Z2, this one was Z3 in the 4th quadrant. And again, if we raise all of these to the power of 3, we should get negative 8. Okay, if we've done this correctly. Okay, which is pretty amazing. I don't know if you want to show your methods friends and do their heads in. And I wish they would have done specialist ins as well. Okay, so how do we use this? We're going to use this special fact to help us solve polynomials in the complex domain. So we're going to think about, we just did something pretty amazing. We found 3 cubic roots of a number that we previously thought only had 1 cubic root. We're going to use that same kind of argument to find solve polynomials in C, basically, in the complex number system. So this is a rule, okay? So the degree of the polynomial tells us the number of solutions we have in the complex number systems. Some can be real and some can be complex, but there's going to be n. Any polynomial raised to the power of n is going to have n solutions, and they can be real or complex, which is not the case for just, when you're doing this in methods. So what does that mean? So for example, a cubic polynomial has 3 solutions, and some of them can be real and some of them can be complex. When you're solving in C, that's important. When you're solving in the real domain, how many can you have? Do you always have 3 solutions for a cubic polynomial? So you've got your cubic polynomial, it can look like that. That's one solution. Or it can, that's one real solution. What we're saying here is, or it can look like that. Can you have 2 or 3? You can have, and you can have ones that look like this. It's 2. So what we're saying is, when we're looking at in the complex domain, we've got a cubic polynomial. It always has 3 solutions. So a polynomial of degree n always has n real or complex solutions. Okay, maybe that's great. There's another rule too. If our polynomial is a polynomial where all the coefficients are real numbers and we happen to find one complex solution, then the conjugate is also a solution of that particular polynomial. So there's a couple of new rules here. There's n solutions for a polynomial of degree n. That's rule number 1. Rule number 2, if a polynomial function has real coefficients and we find one complex solution, then the conjugate of that solution is also a solution as well. So this is kind of important. Any complex polynomial of degree n greater than or equal to 1 has at least one complex 0. Okay, which means one complex root. That makes sense. That's following on from rule number 1 here. Okay, so how we're going to use these two important facts. We're going to use them to factorize polynomials in the complex number system, and we're going to come up with a heap more solutions than what we would in methods when we're just confined to the real number system. So we've got all these different ways of representing complex numbers in Cartesian form. Z is equal to x plus yi. Its conjugate is equal to x minus yi. That's the conjugate of the complex number z. When we multiply, if you recall, the complex number by its conjugate, we end up with a real. Okay, we're going to use this. You just need to remember that. And that's what it looks like when we put them on an Argand plane. We've got our complex number, and its conjugate is just a reflection of that number in the real axis. Okay, so let's have a look at a polynomial of degree 2, which you might also call a quadratic. So polynomials of degree 2, like, oh, okay, this is great. So degree 2, that's a polynomial of degree 2. It's got x squared in it. That's the highest power. X squared plus something or other, or minus something or other, minus 5 or something. That could be that one there. We know that one's got two real solutions. How many complex solutions do you reckon it has? Should I pick one that's got nice, yeah, 0, yes. Because there's two solutions, and they can be, if we're solving it in the real and the complex, so there are two solutions in C for this one. And we can see that they both happen to be real numbers, that's okay. So, here's one I prepared earlier, let me just change that. Okay, so we know this one. This is just the regular quadratic we might have done in year 9 or 10. So we can easily solve that, we can work out what they are. This is 2, 0. Roots, and the other one is negative 2, 0. And there's only two of them. Okay, it's two real roots. Done. What about this one? This could be x squared plus 4, is it? Or x squared plus 2. When we work out the discriminant for this, we don't have no real solutions, but according to the rule we just saw, hey, we've got some complex roots that are solutions for this particular quadratic. So let's have a look at them. So if this was, for example, the polynomial x squared plus 2, there would be no real solutions. But we know we can solve this. We're expecting to have two complex roots because the polynomial is of order 2. And we can easily solve this. How can we easily solve this? We can rewrite it as p of x equals x squared minus 2i squared. Remember? And then we can solve x squared minus 2i squared equals 0. What's that, guys? That's x minus root 2i, x plus root 2i equals 0. So the solutions here, x in the complex number system plus minus root 2i, which, how about that, is conjugate pair. And they happen to be a conjugate pair because all the coefficients of this particular polynomial, the original polynomial, all the coefficients are real. So when we find one complex solution, they occur in pairs, and the conjugate is also a complex solution, which we can work out all sorts of different ways. Okay, is it possible for a quadratic to have one real solution and one complex solution or root? No. Yeah, it's because, it's just not going to work out for us if it has. We're not going to end up with an x squared. Basically, I think that's. Yes, if the coefficients are complex numbers. Yes, that's true, Marco. Yes, that is true. So we could actually make one up. We could play around with it. We could have x minus root 2I, I don't know, and x minus 2. Why not? There's a quadratic that has one complex root and one real root. And we can just expand that, and there we go. We've got one. Done. But the coefficients, if we expand this, we'll end up with x squared minus 2x minus root 2I x plus 2 root 2I. So if we expanded that, and as you can see, the coefficients aren't real numbers. So there you go. It's interesting. Good fun. Okay, so this is just extending this idea. Polynomials of degree 5. That means that x to the power of 5 is the highest term in the polynomial. So they can look all sorts of different ways. We're saying we're going to have 5 real and complex solutions. So you could have 5 real solutions if you had lots of intersections happening. You could have one real solution, but you've got 5 complex solutions. Okay, so just keep that in mind. So what other combinations are possible for a polynomial of degree 5? 3 and 2, yeah, 3 reals, 2 complex. I think we've got all sorts of combinations really, haven't we? So can we have one complex, 4 real? I think we can. You can see, you can make up your own. Yeah, the coefficients will be complex. But you can make up your own. Isn't that fun? You can make up your own. Alright. Let's use some of these techniques to solve some here. So we're finding the complex zeros or the complex solutions for a polynomial function. So here's one that's a cubic. Alright, so it looks kind of, it's x cubed minus 2x squared plus 4x minus 8, and all the coefficients are real numbers. So that's something we need to note when we first look at this thing. So we can, to find the zeros, we can try factorizing it, because this is just trying to solve, we're trying to solve f of x equals 0 in the complex number system. That's what we're trying to do. So we can try factorizing, and there's all sorts of techniques for factorizing. Maybe you've seen this one called grouping. So you can factorize, and then you can solve that. You can use the null factor theorem to solve the factors x minus 2 is equal to 0 or x squared plus 4 is equal to 0. And then you can progress to finding the solutions. X squared is equal to negative 4. This one is going to have complex solutions for it. And there they are. So the solutions are x is equal to 2 or x is equal to plus minus 2i. So you can see again, the complex solutions have occurred in a conjugate pair because all the coefficients for this polynomial were real. Okay, so, alright, what about more complicated ways of working out? So this is a different one again, this is a different cubic. This is x cubed minus 3x squared plus 9x plus 13. And what are we told here? We're told that I think I must have chopped out a slide here. We're told that if we're told that one of the values, negative 1, when x is equal to negative 1, this polynomial is equal to 0. So you remember from math methods that means that you use the remainder theorem to work out that if that's true, that is true, and that's one of the ones we can just guess by just looking at it, putting in -1. You see there, -1 cubed minus 3 times -1 squared plus 9 times -1 plus 13 is going to give you 0. So we found one of the roots of the 3 roots, and we can do a bit of polynomial long division, which I hope you know how to do. So basically you set out a long division. Do you know how to do this? We've done this before. X cubed minus 3x squared. Have you done this in methods? Do you do this in methods? 9x plus 13. You done that in methods? You can do it that way, or I don't know, I think that's in where you can do it. So you can say, how many times have you done this? Has anyone not done this or wants me to do it now? Do you want me to work out the polynomial long division? X into x cubed, that goes x squared times. Then x squared, you multiply that by the divisor, x cubed plus x squared. Then you subtract it. So that's -3x squared minus x squared, or x cubed minus x cubed, that's 0, minus 4x squared. Then x goes into, bring down number 9, x down here. Then x goes into -4x squared minus 4x times. So it's going to be minus 4x squared minus 4x. So you subtract everything. So that's going to end up being 13x here. Bring down the 13 plus 13. X plus 1 goes into 13, x plus 13, 13 times. Pretty much 13x plus 13. So hard to write with a mouse. 0. Okay, so that's the other, that's just by doing polynomial long division. You can work out what the other factor is, and you can spend some time on that, or you can just use the quadratic formula on that to work out the solution. Okay, so you can do a bit of polynomial long division, so you know that these are the two factors, and maybe use the quadratic formula on the quadratic one. So you can use the quadratic formula, and there you are. Because the quadratic formula, remember, you can still work out if that's a negative number under the square root, you just multiply it by I squared, and then you can find the root of that. And yeah, that's the complex solution. So there are the 3 solutions. You've got your -1 and 2 plus minus 3i conjugate pairs, because the original polynomial had real coefficients. Okay. Okay, so the graph. What's the graph look like? If you did a graph of this, it only crosses the x-axis. There's only one real 0 for this one. So if you drew a graph of this on a real Cartesian plane, you're only going to get one real 0, because you cannot represent 2 plus 3i and 2 minus 3i on a real graph. What does it mean on an Argand plane? What does it mean? It means that you've got these roots here, you've got 0, you've got -1, -1, 2 plus 3i, 2 plus 3i, one's over here, and one's down there, 2 minus 3i. Does your head in, really. Just thinking about it, real and imaginary. Bye, Gabby. Okay. Alright. That's the real 0, or the real root. But we know that in the complex, the Argand plane, we've got 3 roots in the complex number system. Okay, it can even get more exciting. Here's a quartic, x to the power of 4. So, if we're given one of the values, guys, how many are we expecting? We're given one solution for this. Goodbye, Levi. Is 3i. Automatically, we should be able to work out what the other solution is. Bye, Amanda. What's the other solution? Conjugate number theorem says that there's got to be another 0 that's negative 3i. And so we can use that to find one of the factors. And we can just use polynomial long division to simplify and find the quotient, and maybe use the quadratic formula or factorize that if we can to get all the solutions. So there should be 4 solutions here. 1, 2, 3, 4. Okay, 4 solutions there. Okay, here we go. Here's a mystery third degree polynomial, cubic polynomial. And it has real coefficients. Okay, here are they. Here they are. Here are some of the answers. Here are the 2 roots. 2 out of the 3 roots in the complex number system, 3 and 5i, and the polynomial has real coefficients. Big hint, real coefficients, that must mean that also negative 5i is also a root, so we can then work out what all the factors are. X minus 3, x minus 5i, and x plus 5i, and we can expand that and work out what the mystery polynomial was. There it is there, mystery polynomial. Okay, and finally, regions of the complex plane. Okay, this is going to go a bit longer than I anticipated. Alright, we've got the idea we can find the modulus of a complex number that's equal to 5. Basically that's saying these are all the complex numbers. This locus, this line, this circle represents all the complex numbers that have a modulus of 5, that have a centre of 0, 0. That's all of them. There's an infinite amount of them. So the modulus of these numbers is equal to 5. And that's what that would look like. That locus is saying all these values, all these real numbers on that locus meet this condition. And if you think about it, what does that mean? If you put the number in Cartesian form, z is equal to x plus yi, to work out the modulus of any complex number, you work out its distance from the origin, and that's got to be equal to 5. So basically you can convert the locus is the Cartesian equation of x squared plus y squared equals 25 in this case. This is the equivalent, which is a circle with a centre at 0. Okay, what about this expression here? We want to sketch z minus 2 plus 3i equals 3. Again, this is going to be a circle as well, with a radius of 3, but it's going to be off-centre. So we might let w be equal to z minus 2 plus 3i. So we can write w, collecting all the components here, z minus 2 plus 3i, it's going to be z x minus 2 for the real part, y plus 3 for the imaginary part. Okay, and then we can work out, this is translating the locus by 2 units in the real direction, positive real direction, and negative 3 units in the imaginary direction. So let's see how that's going to work out here. Okay, so you can see here, if you worked out the modulus of w, which is the same as the modulus of this. That's going to be equal to x minus 2 squared plus y plus 3 squared. The square root of that is going to be equal to 3. So you can see again how the circle will be formed from using that. Okay, so it ends up being a circle with a centre at negative 2, at 2, negative 3, with a radius of 3. So that will convert into x minus 2 squared in Cartesian form, plus y plus 3 all squared equals 9. Okay. Alright, and there's some other expressions that we can use to work out locuses. So this is saying I want to find all the complex numbers when I add 4 and take away 2i from them that have the argument of pi on 3. So basically we know that if we can find out the complex numbers that have an argument of pi on 3 without being translated would be all the complex numbers on this locus. They all have the argument pi on 3. You agree with me there? Because they all make that angle with the real axis. So what we want to do is we want to take away 4 and add 2i to that to get all of them. So we're actually translating them. So x plus 4, if we let w equal z plus 4 minus 2i, so we replace w in here, we want the argument of w to be equal to pi on 3. Okay, so this is just a translation. We translated negative 4 units in the real direction and positive 2 units in the imaginary direction. Negative 4 in the real, positive 2 in the imaginary. So we've actually just shifted. So these are the numbers that represent, these are the complex numbers on this locus, make this condition true. All those complex numbers meet this criteria and they make a locus. And there's a little hollow here. Why is there a little hollow there? There should have been one here too. Why is there a little hollow there? Has no argument. Yes, because the modulus there is 0. So if you have a modulus of 0, you can't make an angle with any real or imaginary axis. That makes sense, doesn't it? So we don't know what happens there. So we leave a little hollow because that's an unknown little area. Okay, so what about some more of these? Have I got time? Is this the last one? Or this might be the last one because I don't think regions are in this anymore. Okay. Here's one that's a little bit complicated. Show the locus that is defined by this condition. The modulus of z minus 2 plus I is equal to the modulus of z plus 3. It's going to be a straight line. We want to find its Cartesian equation. So z minus 2 plus I is the modulus of that is going to be a value. When is that equal? When is this distance equal to that distance? Okay, so let's just do a little bit of fancy algebra to work that out. So the left-hand side, to work out the modulus of z minus 2 plus I, we just replace z with x plus yi, and we work out its modulus. So we're just going to do that. That's going to be x minus 2 all squared using Pythagoras' theorem, y plus 1 all squared. To do that for the right-hand side, z plus 3, the modulus of that can be re-expressed as x plus yi plus 3, and we can work out the modulus of that side. And we can equate them together. When we equate them together, we can square both sides, square the left-hand side and square the right-hand side, and we're going to see we're going to end up with an expression. Quite a lot of terms will cancel out. All the squared terms will cancel out. So x squared will cancel out with the x squared on the right hand side, y squared will cancel out with the y squared on the right hand side, and we end up with a linear equation, which is the Cartesian equation of the locus. So what does that mean? What does that mean? What does that mean? This locus is all the points on this line are equidistant from, say u is equal to 2 minus I, so that's u, and v is equal to negative 3. Oops, hang on, I've got u in the wrong place. U is over here. Get rid of that one. Get rid of that one. So this is u down here. 2 minus I, and v is equal to negative 3. V, this is 2 minus I, and v is equal to negative 3, plus 0. And this line here, 5x plus 2, and I think the animation will show it. I can draw a straight line with me. So there it is, and there is y equals 5x, that's y equals 5x plus 2, and this line meets this criteria. All the points on this line are equidistant from those 2 points. What does that mean? What does that mean? Any point here has the same distance. Any point on this locus is equidistant from u and v, and u and v are formed by these translations from the complex numbers here. So they're all equidistant. And that's it. And the regions aren't really in it, but you can have a look at them in your own time. They're just inequalities. I'll just quickly go through them. They're just inequalities that you've done before, but I don't think they're officially in the course anymore. Okay, so that's it for today. Thank you for listening, everyone. Bye for now. Bye.